In this video, we'll introduce a different type of autoencoder known as the denoising autoencoder. We talked in the previous video how an overcomplete hidden layer in the regular autoencoder doesn't make a lot of sense in terms of what we can expect the autoencoder can learn. And that's because it could actually just learn to copy individual elements in the input vector, and then h of x would just be a copy essentially of the input, so would not necessarily be encouraged to learn meaningful features. And so now we'll see that with this new formulation known as the denoising autoencoder, we will get a set of hidden units which extract interesting structure from our training set. So the idea is actually quite simple, and we'll see that it essentially directly addresses the problem that an autoencoder could learn, a regular autoencoder could learn to just copy the input. So the idea is to train, so the model is known as the denoising autoencoder, and you'll see very clearly why it's called like that. So the idea is to learn a representation extracted by the encoder that is robust to the introduction of noise into the input. And so the idea will be that instead of feeding to the encoder the original input x, we'll actually feed a noisy version of it. And this noisy version, which I'm calling x tilde, is going to be the result of taking x and then passing it through a noise process, so some probabilistic process which will take x and then generate this x tilde in some way based on x. So one popular way of one popular choice of this noise process is to just randomly assign certain elements of the inputs to 0, where we'll choose to assign an input to a value of 0 with some probability, which is a hyperparameter we would have to tune. So in this example here, say the probability was half, then we would iterate over the inputs, and then say for this input, I flip a coin. Maybe the coin says that I should add some noise. So in this case, instead of copying x, I would actually not copy it and set the value of that unit in x tilde to 0. Here I flip a coin, I get a different outcome which says copy, so I copy it here. Here I don't copy it, and again for all, and so on for all the input elements. So we do this sort of randomly. So if we did that another time for the same input x, we get a different pattern of zeros. And that's actually crucial. So now what we've done is that we're feeding to the autoencoder a noisy variant where some of the elements for this noise process has been essentially erased in a sense. We could choose other types of noise. We could add Gaussian additive noise by adding, say, Gaussian noise with a mean 0 in a particular variance, which would be a hyperparameter we would have to tune. And then to train the denoising autoencoder, so from x tilde we get a encoder value h of x tilde, and then we get a reconstruction x hat. And now x hat, we don't compare it to x tilde, we actually compare it to the original input. So the loss function compares x hat to x, not x tilde. And now we see that in this case, for one thing, we can get a perfect reconstruction error by just copying x tilde into different units here. So for instance, because the autoencoder gets a 0 here, but this 0 was actually the result of some noise, then at the reconstruction, if it's trying to actually reconstruct that value, it can't entirely trust this value, because in this case actually it's 0, so it's actually not the right value. You cannot just copy at the output the value of 0. That would be a terrible prediction to do in terms of the loss. So instead, the denoising autoencoder will be forced to use other inputs, so for instance that input and that input, to and then learn about what's the relationship normally between these two inputs, say, and this other input here. And then using by learning what that relationship can be, then it might be able then to infer a more reliable prediction of what this input was based, say, on these two inputs. So that's what the hidden layer will be forced to try to do, and this will thus force it to have hidden units that extract particular types of structure that we tend to see. So different types of correlations between the inputs that we tend to see in the input vectors in our training distribution. So by doing this, we really broke and made impossible or not optimal this behavior in the autoencoder of just copying each input because there's noise in it. So by adding noise, we're forcing it to learn about the structure of the input distribution, and then we're forcing it to also, at the same time, learn more meaningful features, as we'll see in the next slides. So here's an illustration of how it's training. So imagine in this cartoon example that we're reconstructing vectors in 2 dimensions, and that our training distribution is such that really all examples sort of lie around this one-dimensional manifold. This one-dimensional curved line here essentially corresponds to where almost all of the data from my input distribution lies. And when I'm training, what I'm doing is that I'm taking one of these X training examples, so these different X's would be samples in my training set, and then I'm adding some noise, so that's pushing it away from the manifold. And then what the autoencoder is trying is to take this X still, which has been pushed away from the manifold, and project it back on the manifold. Especially, it's trying to project it exactly to X. And so on average, what it's going to do is sort of try to push back the data where most of the training data usually is. And so by doing this, really it's learning about this structure. So in this case, the structure of the data is essentially the shape of that manifold. And so we see here in this visual illustration that we're forcing the autoencoder to learn about what that structure is, because it needs to know what that structure is in order to know where to project back the noisy inputs X still to be able to get a good reconstruction X hat. So for our images, we wouldn't be in 2D, but for images, we do have the notion that most images lie on the lower dimensional manifold, which represent variations such as translations and rotations and small deformations. And so if this was an example, then a noisy example would look something like this. It would kind of look like a character, but not exactly. It would be slightly off the manifold. And then we will learn to push this back into this here. And again, in a sense, we're also learning to distinguish between true inputs and noisy inputs. If we had a lot of noise, then we would be generating something like this. And so we'd be learning essentially that we don't want to be able to reconstruct this perfectly. What we want to be able to reconstruct perfectly is things that look like digits like this. Even if they have a little bit of noise, we'd be able to reconstruct them back into a nice looking digit. Whereas this, which has a lot of noise, we would not learn to reconstruct it into its own noisy version. So again, we fall back in the setting where we have hidden units that are good at reconstructing things that look like the data, the training data, and that it's not good at reconstructing things that are very noisy, because noisy things like this or less noisy things like this are going to be projected back into a non-noisy image. So let's look at the actual features we get when we train on MNIST. So this is an example of features trained by an autoencoder without corrupting the input. So that's just a regular autoencoder here. Now, if we take 25% of the input, and we set it to 0, so we have this masking noise type of corruption, then we see now that a lot of the hidden units, their filters, start looking more like edge detectors. For instance, we have these sort of pen stroke-like detectors here, here, and here. This is also kind of like a pen stroke detector in the sense that we have some ink here, and then it's saying there's background right besides the ink. We also notice that the filter, for instance, this one, which was not looking too bad, is now, so if you keep your eyes on this one, we see that now the filter actually got bigger. And that's partly also because if we add a lot of noise, like 25% of noise in the input, then each unit, to be able to say what kind of structure is present, is it a sort of edge like this, then it needs to integrate out many more pixels because you know, many of them might be noisy. So you want to cover enough that you have enough in your set of pixels that this hidden unit is doing its computation over, so that sort of the noise can be washed out of the computation. And then if we add even more, we get even more bigger filters, bigger receptive fields. So when we're talking about receptive fields, we're talking about the number of pixels for which the weights would is significantly far from zero. So this would be white or black in these images. So we see again that we get some interesting features. We are kind of like pen stroke detectors, and they're actually they're actually again bigger because we've added more noise. So it's trying to cover a larger part of the image to be able to extract and figure out more accurately what the structure is. And we get again like a lot of these sort of pen stroke detectors here and here that we didn't get without any noise. Here's another experiment where we train on natural image patches. So we take a natural image like the image of a forest or something like that, and then we take small windows or patches of pixels. So these are like a few pixels by a few pixels only. So they're very small, tiny images extracted from a larger image of a natural scene. And if we train an autoencoder with the square difference loss, and we add Gaussian noise, then the types of filters we get are really interesting. They look a lot like edge detectors. So they're like high intensity or positive intensity, I guess, yeah, high intensity compared with low intensity. So for instance, this would be active if we get something, you know, high intensity pixels next to low intensity pixels. So that's really an edge. And if we actually had trained PCA on these images, so we're not showing these here, but that's not the type of filters we would get. We actually get a lot of these sort of spatial high frequency filters that we saw in the regular autoencoder, where some of the filters were mostly gray, and we saw like small ridges, kind of waves in the filter with high frequency. So we would see these types of things if we actually trained a PCA model on the same images. So now we see that we don't get that for denoising autoencoder, the optimal solution is PCA. It's actually a very different solution which extracts features which are much more meaningful in terms of the types of things we'd like to know about the image, say for recognizing objects. So detecting the contours of an object should be useful for being able to identify what's the nature of that object. And also, it's not equivalent to taking the regular autoencoder and adding a lot of weight decay. So I'm mentioning this because it's been shown that adding Gaussian noise in the input of an autoencoder, if this Gaussian noise was very, very small, then in the limit of towards being zero, then it's essentially equivalent to some sort of weight decay or regularization on the weights. And but in fact, if you trained a regular autoencoder with some weight decay, we actually don't recover the same solution. We get these high frequency filters that, for instance, we got on the images of characters, for instance, that are more, more similar to what we'd expect with PCA, for instance. So really, this is giving a different solution from either strong weight decay or just PCA. This is really a solution in terms of filters that is much more satisfying, and indeed, when we try to use these features for classifying images, we do get much better performances than just with a regular autoencoder. So that's it for denoising autoencoders.